Today I wanted to share with you some of the projects we do, and then in the middle of the research, I will add also a few examples of how the research made it into the real world in different ways. Well, I decided to start from one of the first projects we did. This was 2006, almost 20 years ago. At the time, this was the Venice Biennale. Venice Biennale is a big exhibition about art and architecture every couple of years in Venice. 2025 will be again architecture. Hashim, our dean, curated Biennale 2 years ago, as you might know. And now what we did here in 2006 was actually for the first time take a city and use data from cell phones, from millions of people to see how a city lives. That had never been done at the time. So what we did, it was being exhibited in Venice, so we decided to focus on an Italian city. We picked Rome, the capital. We got the data from Rome, data from cell phone, from taxis, from buses, and so on. In real time, we sent it to MIT, here to the Media Lab, with a number of servers we set up at the time, kind of a proto cloud. And then we analyzed it, we visualized it, and we sent it back in real time, near real time, to Italy. So now we started collecting data such as this. This is actually a very special day when Italy won the soccer World Cup. In 2006, that's the city of Rome. You see the Colosseum, the river, before the match. And people moving here and there in the city. In the moment the match begins, you see it, and silence. Nobody talks anymore. And then France scores. Italy was playing France. Italy scores, halftime. People make a call. And then in the normal time, first overtime, second overtime, a famous headbutt by Zidane, and then finally Italy wins. And then everybody starts to move around and move in different parts of the city and so on. But that was the first time ever actually to use this data for to look at the city in real time. And without the data, we'd not have been able to look in the following years at different things. This paper from a few years ago actually was possible because we took some of the data, similar data to the one you saw, for tens of millions of people. And we discovered something interesting. I will not get into the details, but basically there's an old law of human mobility that shows that if you take two cities, say Boston and New York, and you want to look at the flows between the two cities, they follow some kind of gravity law. So population 1, population 2 divided by a distance power alpha, where alpha is an exponent between 1 and 2. Well, at the time, people could only look at the total flows, but with cell phone data, you can look at how people, not only at distances, but frequencies, how many times people go back to the same place. And when you look at that, you find it beautiful. Actually, you get a beautiful collapse on one single curve. What is very important is not only distance, is distance times frequency. So actually, we discovered this kind of frequency dependency that we've not been able to see without this type of new data we started experimenting with 20 years ago. Another little thing is something that puzzled me since I was a student at Cambridge. This was a college I was in, so Darwin College. And when I was at Darwin, I discovered something that I found very disturbing. And the fact was that I was living here, and I was going to my department, like every student in Cambridge. But I was following one route to go from A to B, from the college to the department, and a different route from going to the department to the college. And that really puzzled me, because if you study shortest path is symmetrical. So if your brain thinks shortest path, A to B is equal B to A. So why the hell I was following? The probability was higher that I would go one way, A to B, in a different way, B to A. And so somehow you could say I was consistently inconsistent. And again, I was very puzzled by this finding. Well, it took us quite a bit of time, but now with data analyzing, in this case, in this paper from last year, analyzing hundreds of thousands of people, both in Cambridge, in Boston, and in San Francisco, we actually saw this is something we all do. Our brain, like the brain of animals, is not coded for shortest path. It's actually coded for something we call here, we define here, pointiest path. Or if you want, well, people, this was together with Josh in brain and cognitive sciences and his team, but basically what with animals people call vector-based navigation. So our brain tries to look at the vector where we want to go and try to minimize angular deviation from where we want to go. And if you look at that, then it's not the shortest path. It's good enough, it's not that different, but that actually leads you to something which is not symmetrical. A to B can be different than B to A. And it is interesting if you think about this. It's interesting for two reasons, I think. First is that because we are becoming more and more hybrid systems, so we follow a lot our machines when we navigate. And then if this follows shortest path and our brain is coded for something different, then there's a disconnect. So as we couple more and more artificial and human intelligence, we need to understand how both of them work. But the other thing is that this is probably an interesting way our brain evolved, because if you think about the shortest path is quite computationally intensive. Well, if you look at the pointiest path, it's very easy to compute, is not perfect, but it's good enough, and maybe it saves a bit of brain power, so that a few tens of thousands of years ago, when all of us, when our ancestors were in the savannah, you can look at a lion or other dangers on the way. So it's very interesting about how our brain evolved. But other thing you can do with this type of data from the city, when you look at this, is actually taxi, similar data, not cell phone, but taxi from GPS, pickups, and drop-offs. Which place is this in New York? People from the lab can, there's a few people from the lab, so can, anybody, any ideas? Yes, I heard of JFK, but anyway, this is JFK, so if you landed at JFK, you were one of the little dots, a pickup in yellow or a drop-off in blue. If you look at this, it's actually the same image. JFK is down there. You see all of Manhattan and all the boroughs. If you look at the map in detail, by the way, you don't see, there's no roads. The roads just emerge because of the sheer density of pickups and drop-offs. What you see here is actually just black with water in gray, and then what you see, the structure of the city, is simply the result of all the activity that happens in it. And then in this case, this is quite an old paper. It's a paper, we looked at this, started looking at this over 10 years ago. We started asking a question. Again, this question was inspired by something I think all of you have experienced. You are in New York, you are in a hotel, you're there with your trolley in the morning, you're going to the airport, to JFK, and next to you there's somebody else with a trolley. They're also going to the airport. They could have shared a taxi, but you simply didn't know. So we wanted to quantify how many trips we could share in New York between people. And if you look at this, for instance, between those 2 points in Manhattan, but any 2 points in Manhattan, you got hundreds of thousands of trips over the course of the year. This means thousands of trips every day, which means potentially a lot of trips could be shared by two people going more or less in the same directions. Well, we looked at the problem. We got all the data from the city of New York. Incidentally, the data was made accessible by Bloomberg when he was mayor. I remember in his office at City Hall, Mike had a sign that said, "In God we trust, everybody else bring data." And so what he did in City Hall was actually force his people to share as much data as possible, including the data we got for this project. Now, when you look at this, if you are, a lot of you probably are engineers, you might think I can look at this with linear programming, but linear programming fails to look at how many trips you can share. Linear programming fails when you got so much data. So together with Paolo, together with Steven Strogas, who's a mathematician, you might know Steven is at Cornell. He's one of the fathers of modern network science. We say, why don't we develop a new way to actually look at this kind of big data sets, how we can analyze it? And we developed this system that is widely used today in many mobility problems called Sharability networks. I will not get into the detail, but I use network science. What you see here, those networks, they densify if you allow for a longer delay in arrival. So how do you frame it mathematically? Mathematically, you frame it like you see here in the upper left graph. On the x-axis, you got the delay, because clearly if you pick two people, they go more or less in the same direction, you introduce a small delay. But then we look at, even with a small delay, which is what you see, which is this in seconds, so 1, 2, or 3 minutes, then you can share a lot of rides. And it turns out that with a delay of maximum 3 minutes, you could cut fleets in New York by 40%. Something interesting happened, and here I'll get back to this point, the fact that, how do you turn research into something that has an impact? Yes, sometimes you do a startup. I will show some examples of that. We've done quite a few with patents filed at MIT with TLO. But in other cases, maybe you just inspire somebody. So when we did this, we published it, we did a website, and a conversation started. And that's always good. Conversation is like feedback loop. The New York Times did the review of the results. There was an article. Nick Fox, the science editor for the New York Times, wrote a great article, but he said, yes, all of this is good, but New Yorkers really don't want to share anything. It turns out it was not the case, because a few months later we got a call from Uber. It turns out the founder of Uber had seen the paper, and we did a first collaboration between MIT and Uber, signed here by, not by TLO, by OSP at the time. And we started working with Uber, and as you might know, Uber Pool is what today does that. Uber Pool, now called Uber Share, allows people going more or less in the same direction to share a ride. And that has turned into quite a big, how do you call it, a big product, not only for Uber, but for many other companies, for Didi in China, for Grab in Southeast Asia, for Ola, for Via, and so on. So somehow, sometimes it's enough to do research, and then that can trickle down into the real world. If you want, we can talk about Uber Pool, Uber Share. At the beginning, I was very excited because if you combine 2 trips into one, it means one less car on the road, which means less congestion, less pollution, less emissions in our cities. It turned out a bit differently because if you lower prices, it also means you're taking people out of the subway or the bike and you're bringing them into the car. And I wrote an article about that in the San Francisco Chronicle last year, really saying that unintended consequences should always be looked at. Somehow at the beginning we thought we were doing something good to make our cities more sustainable. In the end, the story turned out a bit different. But anyway, we look at this, we look at shareability around cities. At the beginning is this only New York? Does it apply everywhere? So we looked at data from cities all over the world. Here, if you want, there's some of the results inside. I put just the first page of the papers. You can feel free to look at them. They're all on the website, on our website.